Welcome to my talk with the topic Incremental Automation of Anomaly Remediation in Cloud Computing Environments. And regarding this talk, at least the first part will be a core of my thesis, which is Incremental Automation of Anomaly Remediation, and therefore I am looking forward to your feedback afterwards. The main motivation for this work is that IT infrastructures are growing in size and complexity. Today we have globally distributed data centers, which are already very hard to operate, and future technologies like regional clouds, edge, IoT, and 5G will further increase the distribution and the complexity of IT systems. This basically, from an operator perspective, this leads to a human scaling problem, and we have numbers from one of our industrial partners that state that you need approximately one operator for 100 servers, and therefore 500 operators for 50,000 servers, and these numbers are actually for central data centers. They will be higher when you add regional clouds and edge and IoT to this to your IT infrastructure. From an operator perspective, operating or working with such systems means extreme stress. You have 24/7 shifts and you need to work under very high pressure when actual problems occurs, because every minute that you're not able to solve the problem will cost the company you're working for a lot of money. Additionally, as an operator, you often have tedious tasks like diagnosing a problem by searching through millions of logs in order to find that one particular line that was responsible for a certain problem. Or you have also repetitive tasks like performing a rollback due to a problematic software update. Therefore, a recently emerging research field is trying to introduce additional intelligence into the deployment, operation, and administration of IT infrastructures. Basically, it is trying to merge the previously distinct fields of AI and machine learning with the operation of systems. And the short-term vision is to support system operators by introducing data analysis and automation. And the long-term vision is that someday it is possible to completely autonomously operate complex and large IT infrastructures. From a high-level perspective, such systems are usually designed as closed loops, where the concrete system parts depend on the objective of the system. In our case, we would like to consider the objective of fault tolerance, and therefore the system parts should detect and possibly remediate occurring problems as soon as possible. Therefore, the first step consists of different data analysis methods that are executed on system monitoring data, and this also includes the option to run diagnosis, for example, to get additional data when it's required. Whenever problems are detected, the next step or the analysis results are forwarded to a component that should make a decision in order to select a concrete action that should be executed in order to fix the problem. And this is also where the human in the loop is usually interacting with the systems by either correcting wrongly detected problems or by selecting a certain action from a list of feasible actions during a certain situation. The next step is to schedule and execute these actions on the system in order to fix the problem. And recently there's a strong focus on visualization and interpretability, because when operating critical systems, it's very important to actually understand why certain decisions were made. Within this work, we will focus on the intersection of data analysis and decision making. Based on related work in this field, data analysis steps can be grouped into 4 groups. Usually, the initial data analysis group is the anomaly detection, which has several requirements. One requirement is that it should be able to detect previously unknown anomalies, and therefore it must be unsupervised. Additionally, it should constantly analyze incoming monitoring data streams and must therefore operate online. And as much as possible, system parts in my system should be covered by the anomaly detection, so it third needs to be scalable. This puts several complexity constraints on the underlying models. The next two steps are alarm aggregation and localization, because in distributed systems several system components are interconnected and interact with each other, and therefore occurring anomalies are usually affecting groups of system components. There I need to aggregate anomaly detection alarms that are temporally correlated, and I need to localize the problem origin. Another data analysis step group is the anomaly type classification, where it's required to assign descriptive labels to detected anomalies. And this work actually focuses on the anomaly type classification. So why it's important to assign descriptive labels to detected anomalies? Because basically this enables us to do two things. First, it's possible to identify reoccurring anomalies that were remediated in the past already, and therefore by assigning descriptive labels to these reoccurring anomalies, we can map them to a set of feasible remediation actions, which can be either executed automatically or presented to system experts as options. Additionally, as I previously said, we have an anomaly detection or an initial anomaly detection that is restricted by complexity constraints. This results, and it can be observed in related work, in considerable false positive rates, and currently one very high objective is to reduce false positive rates in anomaly detections. By assigning a descriptive label, for example normal, it's possible to correct false positive detections. So overall, since we are operating on systematic data, which are basically multivariate time series, this problem boils down to time series classification. And since the systematic data are updated continuously, we also need to continuously update our classification, and therefore we have continuous time series classification. Concrete related methods are dealing with this problem in three different ways. The first option is to have an anomaly detection, which is a multi-class classifier. Therefore, the requirement of being unsupervised needs to be dropped, and the models that are employed there are usually far more complex, which limits their scalability. Another option is to not have a classification, but only the binary decision whether a certain system part is in an anomaly state or normal. This pushes the responsibility to the decision making, and there it is usually assumed that every occurring anomaly can be fixed by executing one generic remediation, which is from a practical perspective not realistic. And the third option is to have a two-step approach. First, to have a binary anomaly detection, and second, to have a multi-class classifier in order to assign the label. We would like to follow this third step. Based on this, the objective can be summarized as follows. First, the continuous monitoring data stream is analyzed by an anomaly detection, which outputs a binary label, so either normal or anomaly. Whenever the label is anomaly, we employ a continuous time series classification, which outputs a probability distribution of over all classes Ci conditioned on the multivariate time series X. And thereby the constellation of the class label C is important. It consists of Ca, which is a set of all previously observed and therefore known anomalies, the class Cn, which is the normal class, and it's used for correction of the binary anomaly detection in order to reduce false positive rates, and Cu, which is an unknown class. For this class there's no mapping to a feasible remediation set. And for these systems, it's especially important to clarify the questions on how to deal with unknown anomaly classes. The handling of previously unseen and therefore unknown anomalies can be done by two extrema. The first extreme is the complete automation, where a trial and error approach is employed. Thereby, previously unknown anomaly types are handed over to the decision making, which then starts to arbitrarily execute remediation actions and closely observe their effects on the system. Whenever a certain remediation was able to resolve the anomaly, it stores this as into the set of feasible remediations for this specific anomaly type. Another more safe approach is to employ the human in the loop. Thereby, previously unknown anomaly types are handed over to system experts to fix them, and by interacting with the system actually learns which remediations the experts executed for fixing this anomaly, and therefore this can be saved to the set of feasible remediations for this anomaly type. So whenever the anomaly type reoccurs in future, it is possible to select the remediations that the human experts previously executed in order to fix it. This also shows, or this results in a knowledge transfer from human operators into the system. And this is also where the title of this work came from, which is Incremental Automation of Anomaly Remediation. So the system gradually learns which actions need to be executed for which anomaly types. In order to solve the problem of assigning descriptive labels to detected anomalies, we propose the following model architecture. At the bottom you see the continuous monitoring data stream, which is used as an input. We rescale each metric there to a range between 0 and 1 as the only preprocessing step. The next part is a recurrent neural network consisting of GRU cells which are regularized by a dropout. Here you can see that we are showing or visualizing the recurrent neural network in an unfolded way in order to visualize the flow of each continuous monitoring data stream element through our model architecture. The last element of the recurrent neural network is a linear layer, which maps the output dimension of the GRU layer to the number of classes that we need to classify. And this is done actually by softmax distribution over these classes. Until here, we are able to classify the anomaly types which are elements of the set CA, so all known anomaly types, and also the normal class. The unknown class is not directly classified, and therefore we are using an element which calculates the Gini coefficient. This is actually a measure for non-uniformity of the softmax distribution. This assumes that whenever the softmax distribution is more or less uniform, the model is not confident into the current decision. So it does not concretely know which label to assign to the current continuous monitoring data stream. And therefore, whenever this occurs, we expect or we assume that the current anomaly type is unknown. The next part is the concrete label assignment step, which employs an exponential smoothing in order to mitigate some outliers during the classification process. You see that we are actually outputting the classification results in an online way, similar to the way that we are receiving the continuous monitoring data streams. One important requirement for the proposed model is that it should generalize well with a low number of examples. This actually reflects a faster ability to automate remediations, and also in general we expect anomalies to occur rather infrequently in our system. But whenever you train recurrent neural networks with a low number of examples, you usually observe the problem of overfitting. And on the right part you see a diagram that actually shows an example of such an overfitting problem. The x-axis represents the number of epochs, so the number of times the model were presented all the training data that are available. and on the y-axis you see the loss, which is a measure of how well the model performs on the classification task. The blue line is representing the loss for the training data, and the orange line is representing the loss for the validation data. So the model was trained on the trained data, and therefore the loss is constantly going down. But the validation data, or for the validation data, the model was not trained on them, but they were used to do the prediction and in order to measure how well the model is performing generally. So not only on the concrete training data, but also on examples that were previously not seen. And you see that the model is performing quite well on the training data, but whenever it observes examples that were not directly, or on which it were not directly trained on, it performs poorly. In order to mitigate this problem of overfitting, we developed a time series augmentation method consisting of 2 steps. And this is visualized conceptually by these 3 diagrams. In diagram A, you see 2 classes, the red class and the blue class, with each have 4 examples. Please note that each point is representing a multivariate time series here. And the first step is some form of a local blurring, where we utilize the underlying noise of these examples. Therefore, we first are applying an STL decomposition, which is a seasonal trend decomposition. And on the remaining residuals, which are assumed to be the random noise, we apply a tempered block bootstrap to sample from it, and then reversely combine the trend part and the seasonal part into a slightly changed, so with a different noise, time series. This you can see in diagram B, where each point, or where are these rectangles, which are these augmented examples that are originated by the respective red point in the middle. After that, we are using a pairwise interpolation based on discrete time warping barycenter averaging, which is an actually possibility to average 2 or more time series. Therefore, we randomly select 2 neighboring examples, and there we randomly select a certain number of this locally blurred generated examples, and then use them for this discrete time warping barycenter averaging, and therefore create examples that lie somewhere in between these 2 examples, and therefore this is some form of interpolation. You can see this on the diagram C on the right part. To test our proposed solution, we built an evaluation test bed, conducted experiments, and collected data sets. It is based on the use case of cloud computing environment, and our test bed is basically consisting of OpenStack and Ceph. On top of it, or on top of the virtual machines that were deployed there, we deployed 2 services, which are an RTMP video on demand service and a virtual network function service, basically virtual implementation of the IMS core. So in order to represent a more realistic environment, also with interferences between different services, we deployed both services in our experiment. The overall experiment runtime was 72 hours, and we used an Anomaly experiment controller in order to variate the load and in order to synthetically inject 7 anomaly types on the hypervisors and also on the virtual machines. We injected the anomalies for 5 minutes. After that, we deleted them again, and we have in between the injections a 1 minute of grace period where the system were operating normal. First, we analyzed the effects of the time series augmentation on the training of our model. Therefore, we trained our model on 4 examples of each anomaly type and used 2 examples for validation. At the bottom you see the results of the different constellations for the time series augmentation on the training process. On the left part you see the results where no augmentation at all was used, and here it is clearly visible that the model overfits on the training data because the validation loss and the training loss are strongly diverging from each other. In the middle you see the loss for the or with the STLR augmentation, where both loss, so the training loss and the validation loss, are closer to each other. However, the validation loss has a high variance, therefore the training process is not stable. On the right part you see the proposed solution consisting of the STLR and the DBA augmentation. Hereby you see that the number of epochs increases until the model converges, but the training process overall, or the model, does not overfit, and the training process overall is rather stable. Next, we analyzed the classification results for the CA classes. This means that we assumed all anomaly types as known and therefore trained our model on 4 examples of each anomaly type and used the remaining 2 examples for testing. We additionally applied a complete fault cross-validation in order to test all different combinations of test and train data. The diagram show the point-wise accuracy. On the left part you see it per anomaly type, and on the right part you see it per node group. For the anomaly types, you see that the model is able to classify the different anomaly types with a high accuracy. However, there's one outlier, which is the memory leak anomaly, with a slightly reduced pointwise accuracy metric. The reason for this is that the anomaly, or the anomaly type memory leak, is a gradual anomaly and looks very similar to the normal state at the beginning. So the first few examples of these, or the first few monitoring data stream elements, are usually classified as normal instead of memory leak. This is actually the explanation for the reduced performance here. On the right part you see that there's no significant difference between the different node groups in our system. The outlier at the bottom, which looks a little bit like raindrops, are all belonging to the memory leak anomaly type. So these are the points where the memory leak anomaly type was misclassified. Next, we used the trained models in order to analyze the classification results for the CN class. Therefore, we employed an example anomaly detection and counted the number of false positive predictions, which you can see in the first row of this table. The columns represent the different system components of our system. The second row are the successfully corrected false positive predictions by our model. You can see that we were able to successfully correct 293 out of 313 false positive predictions, which corresponds to 94%. At last, we analyzed the classification results for the CU class, means the unknown class. Therefore, we trained our model on all anomaly types except one and tested whether our model is able to predict the left out anomaly type as unknown. You can see that our approach is able to classify the unknown class with an accuracy of 97 to 99%. And again, the problem here is basically the memory leak anomaly, which again at the beginning looks very similar to the normal class, and therefore the system usually predicts it as normal until a certain point where it starts to significantly deviate from the normal class, and then the prediction switches to the correct unknown class. In summary, we introduced a method to incrementally automate anomaly remediation. Therefore, we presented the model architecture for continuous time series classification and also introduced a time series augmentation method that enables a generalization on only a few examples. Furthermore, we evaluated our work with different services and on different cloud layers, and additionally under different load variations. Open challenges are still different system loads, for example, because if we encounter system loads that were not observed within the training data, the interpolation approach of the time series segmentation fails. Here we would need an alternative approach that is able to extrapolate on previously unseen load variations. Another problem are concept drifts, for example, infrastructure changes like software updates, hardware modernizations, etc. This boils down to the transferability of such models to different but similar systems. We're still working on this. Thank you for your attention, and I'm looking forward to the discussion with you.